So hello and welcome back. We're there at this lecture after a heavy dose over that dealt with the entire paradigm of the artificial neural network. So just to give in a glance, we first designed a model that was capable of taking any shape, that was capable of doing some heavy amount of regression as and when required. This was the artificial neural network that we saw a couple of lectures back. And after that we said that there was a need to tune in the various parameters because they were initially set any kind of randomly in nature, and there were many of them. So for that we introduced the term of learning. Now in the term of learning we devised an entire bigger paradigm over the supervised learning that we had already seen. We said that what would be kind of general framework, what would be kind of general architecture. And towards the end we concluded by saying that by taking a kind of steepest descent approach, setting the various parameters called a form of the learning rate, the momentum, the error function and the stopping criterion, in that we could get in a kind of algorithm that can tune the various weights and biases. Of course there were limitations that also we discussed in the previous lectures. They were limitations in terms of what the algorithm would be able to achieve, what it would not be able to achieve. So maybe it gets stuck up somewhere into the local minima without reaching the global minima. Maybe the kind of oscillations are large depending upon the values of the learning rate, the values of the momentum and the other parameters depending upon the complexity of the problem. The only thing that was left in the entire discussion, what we will be taking up immediately, is the mathematics behind the backpropagation algorithm. So again I've got something that I've already written up, so we'll save in a lot more time by having all these equations up already up. So what we had ultimately, the artificial neural network, it was a collection of artificial neurons, and each neuron was ultimately an agent that can sum up and after that provide some kind of function. Let me say this is a simple sigmoidal function which will be represented in this form and providing some kind of output. As per the feedback mechanism, I have already applied some kind of input. I have noted down in the feed-forward state some kind of outputs. So this is that I've already done. So I can simply say that there have been some inputs that were applied over this entire neural network architecture. That's something that I haven't drawn. And based on that I got some output that is already noted. This was called as a feed forward stage. I just need to design a feedback stage that I already said will flow in some kind of error layer by layer. This is what we've already seen. Of course not the input here, this is a passive, not after this because the input layer is a passive layer. So this I've already said that the errors need to backpropagate as per the general working methodology of the backpropagation algorithm. We need to design our equations such that we can find out from the feedback what this kind of error would be. Now let me break it up into first the output layer. The output layer will again have this kind of a structure where there's summation unit and there's a function. I consider any one of the possible outputs, each one of them can be analyzed separately. So here I have a kind of output that is already available with me. I have a target that was already available with me. When I applied the feed forward stage, I noted down all these outputs by the various neurons and ultimately got in the output of this neuron. This was already available. This I calculated up from the feed forward stage. I already had a target with me that I had. My error will be naturally called as target minus output, and this is what I propagated behind. This is what I will try to propagate behind at this output layer, at this layer. This is what I will try to propagate behind. So when I try to propagate behind using this kind of approach, then I simply need to find out a gradient. That will be a derivative of this. That will give me the gradient because there is an activation function over here. I need to calculate this gradient. And when I apply this to the error, I get this delta term. When this gradient is applied to this error, this t minus so is basically the error, I get this delta term. Now mostly I will be able to say that what my derivative is of this activation function, it can simply be represented by an output 1 minus output. That's what I can approximate my error function in order to work upon further. So this will give me some kind of delta that I need to basically backpropagate from one layer to the previous layer, from the previous layer to the previous layer. I'll keep on propagating this delta. At every layer I'll calculate the delta. I'll try to move backward. I'll again try to calculate the delta. I'll again try to move backward. And using this delta, the second thing I will do is to try to adjust the weights. So I have two jobs to do is to calculate the delta for the layer, and then using this delta I try to calculate the modification of the weights. Now first let me take the problem of modification of the weight, since there's some kind of delta that's already available that I'm bipropagating. So considering this delta available, I say that I need to calculate the modification of any weight. Now the notation used is PQK. It means the weight that exists between a neuron P and a neuron K and a neuron Q, such that the neuron Q lies at layer K. So this I have as my layer J, and this I have as my layer K. Let this be the pth neuron in this layer, and let this be the qth neuron in this layer. So this will be represented by WP, P the neuron of this place, Q the neuron of this place, and K the layer over here. Let this be the notation being used. So I need to find out, in trying to propagate the error backward from a layer K to a layer J, what is it that the modification need to be made. So I took up any one of the random weights, again because I am using a PQ notation as general, between any neuron P, any neuron K and any layer K. K is the forward layer when it comes to seeing it as a feedforward stage, or the backward layer when it comes to seeing it from the feedback stage. So this will be simply given by the modification of weight by this gradient descent approach. Now what the gradient descent approach says is that the modification of weight is given by its delta that exists for the neuron K, that means for the neuron Q and for the layer K. So for this layer I need to find out at the layer K, the qth neuron, what is the delta, and this when I multiplied by the individual output of the pth neuron at the jth layer, I multiplied it for the output of this neuron over here that exists at the jth layer, on which I am trying to calculate the modification of weight, and the pth neuron, the exact neuron being considered. I'll try to find out what my change in weight is. Now the only thing that I have done, I have diminished this entire gradient descent approach. I have diminished is by a multiplicative factor. Of course, eta is between 0 to 1, so it is that whatever difference comes out to be, I am trying to diminish it up. I am trying to control this up, I am trying to curve this up. I am not trying to move in randomly. I am not allowing it to make large modifications of weight. So only because of this term that has been introduced, the algorithm is not allowed to make heavy changes. Else this delta over here, this error could have been maximum, especially during the initial stages of the algorithm. Now because of this large delta, because of this large error, when multiplied by the actual system output, the change would have come out to be massive in nature. Now I am curving this up by this factor that is known as the learning rate, and hence it can be said that when it can now be numerically said when the learning rate is large, the changes will be large. It will try to propagate up early towards the local minima, and when the changes are slow, it will move very, very, very slowly in nature. Now the new weight is simply the old weight plus the change in weight that we have introduced. So this change in weight, it gets up over here, and when added up towards the previous value of weight, I get the new weight. This change in weight, depending upon this delta, and of course even this output, it can be positive or negative. So I can go forward, I can go backward into my error space. E is a notation used for the epoch number over here. So one thing I have done is that I have calculated the weight. Now the only thing I have to do is that I have to traverse the delta backward. I have to devise some ways in which I can calculate the delta backward so that I can work over with delta. Now we use some kind of submission tool over here. When we were working out with our algorithm, we use some kind of submission tool in the feed forward stage. The same kind of thing that we apply when it comes to the backward stage as well. That has been represented out here. So there were two parts of it, the submission and derivative. So to calculate the error that will be propagated backward, to calculate the delta that will be propagated backward, all I do is that I make these errors, individual deltas of these algorithm traverse backward. I make them traverse backward, I take the weighted sum and I take up the derivative of this function over here. So there are two terms that you can clearly see. One term that is denoting the weighted difference of the deltas, that is the delta being traversed backward, traversed over all the neurons over this layer K and multiplied by the corresponding weights that these connections have. So I am taking the weighted addition over here. And what I am doing is that I am simply multiplying it by the derivative of this activation function. I am multiplying it by the derivative of this activation function. This is simply f dash. And of course f dash I will assume to be the output into 1 minus the output. The same thing that I had done at the output neuron over here. This is what I will assume the derivative to be. So now the actual algorithm is very simple. It just says that you start from the output layer, calculate its error, you calculate its delta, you calculate whatever change, then you just propagate delta backward. By propagating delta backward, I need to modify the weights as per these deltas, calculate the new deltas of the next layer, you traverse backward, and then from output layer you simply come up to the input layer, and then all the weights are modified as per this equation out here. All the weights are calculated by this equation out here, and hence you will get that as you move backward with the layer by layer architecture, all the weights will get optimized and they will all get tuned as per the methodology we discussed earlier. The only thing that we have not touched upon over here is the term momentum, which I can simply say that delta WPQK will be equal to all these exciting terms that we have, the reduced by the learning rate, the output and the delta, plus I apply another factor to it, the factor of momentum, and what this factor of momentum, so basically my WPQK at any time step e plus 1 will be equal to my previous, as per this occasion, the delta, plus again this momentum factor Fm. What I will eventually take out is that the momentum drives the system moving in the same direction. So basically I will get the momentum term as reduced by the term alpha, which was earlier, which is also represented by MC in the earlier session I represented by MC, it's also represented by the term alpha. This is called as the momentum. And by the way, it's the change in weight over here. So whichever direction it was going, this circular direction it was going, it's bound to go in the same direction over here, modified by this momentum. So my entire equation that will come out to be of the change in weight, my new weight WPQK will be equal at in time t plus 1 will be equal to my weight, change in weight TQK at in time E plus the momentum factor. The momentum factor I'll take out to be the alpha times of the change in weight of WPQK at time, let's say E minus 1. This is what the modification would be, and this is called as the momentum. If the momentum is very large, this will dominate this term, and the intrinsic ability of the neural network, the intrinsic kind of movement of the neural network would be keep on moving in the same direction if this term is large. If alpha is very small, this term will over-dominate this, and therefore the neural network will go up for the gradient approach. And therefore, as I said, controlled by the learning rate, there is a trade-off between this term and this term when it comes to oscillating between the around the local minima. The learning rate might try to converge it, and the momentum might try to keep it as out as possible. And that's what happens because momentum is large. Whenever the system has deeply converged into some point, the momentum term dominates and it tries to take the system out of the convergence limit. So when it's like your system is not moving at all, it has already converged, the momentum will get dominated, the momentum will dominate and try to take the system out of convergence. So this was more or less about the backpropagation algorithm we've seen with a decent degree. Of course, what was presented was just the final equations. There was no derivation done. The derivation of it is very rough mathematics that again will get it well established into the literature. There are some long rules as how do we get in all the different equations. What we've done is that from a very global view, we've seen that how the delta behaves and we've taken a deep inspiration into the algorithm that would probably enable you code it up, if not understand it to the fullest extent. There are some algorithms we haven't discussed it over here that belong to the mathematical domain. Now, by this training algorithm called as backpropagation algorithm, we've done one thing, that given a structure of a neural network, given an architecture of the neural network, for some kind of point I'll assume that the the activation functions do not have that big a role. Given some kind of given some kind of neural network architecture, assuming that the activation function and the error functions, they do not play a very prominent role, what I've done is that I have tuned my system parameters. What I've done is that I have tried to tune the parameters such that any database given to me in form of inputs and outputs, I'll get the best possible outputs. I'll get the best possible outputs. Of course, this is the supervised equivalent of it, the unsupervised the supervised part of it, the unsupervised where the outputs are not available. We'll see later when we are discussing the self-organizing, that's what changes. There are a slight change in terminology. But assuming there was a supervised learning, given some inputs and outputs, I'll make sure that my error function that calculates deviation between the outputs known to me and the target outputs, my system behaves as generalized as possible. It gives me best output to the unknown inputs. That is what we have just done. But problem is, how do you decide the number of hidden layers and the number of neurons in each hidden layer? I'll speak up let me say a couple of minutes over how these things are decided, and even when I say I'll speak up a couple of minutes over this, I mean that I'm into a very serious discussion. As till date, there has been no algorithm that can, for any given database, try to find out what will be the number of hidden layers, what will be the number of neurons in each hidden layer. There exists no algorithm, and that's why humans are supposed to do it. Now again, when I say that humans are supposed to do it, normally what we do is that our working methodology includes that the data is broken up, as I said, into training and testing. The training may of course be into training and validation. We train the neural network, we generate a random neural network over here. We train the neural network. When we get the neural network over here, we apply the testing data and we calculate the error. When I say that it is a random neural network, I say that a human generated architecture of the neural network, that is what we give over here. We see the error and then we say it will give this user the actual error and he tries to modify it. He tries to get some different architecture. We again train the neural network, we take a look at what is the error, and then again we try to change the architecture. It's a very cumbersome job. It's a very cumbersome job, because not only is the architecture to be specified, but the training parameters, they also need to be specified. So human needs to specify the network architecture and the training parameters, and whatever it does, it finally gets over some error on the testing input. That's a measure of how the generalized system is, and it's needed to do it again and over again. So the important architecture is the training parameter. We already seen how do they behave, how do we generate this architecture. It cannot be a random guess. We need to be very intelligent because this procedure is very time consuming. So total number of tries that you can keep here are highly limited in nature. So we're working with the problem of how do we try to find out the new network architecture. I'll again come up with the basic problem. I'll plot the input space. The input space that said that the output was plotted against some set of known points. Previously I used to write it as the historic data, not from now on I will be writing as the training data. That excludes the validation data because very less of it we are showing it to the system. So there is training data that's already available. How is it that we are trying to fix the number of hidden layers and number of neural layers? Again we will be making the concept of underfit, overfit and the ideal fit. Now, for most of the problems, the number of hidden layers are usually kept 1, so we need not work over it. Under extreme circumstances, when the number of extreme circumstances the problem is not able to learn, you may sometimes consider working over a couple of hidden layers, but usually we keep them as 1. Because what happens is that if I keep the increase the hidden layers from 1 to 2, the complexity of the shape that I can predict, the complexity of the shape, the complexity of the actual neural network that I can have in my system, it increases incredibly. It increases incredibly, and that is what creates a problem. The number of neurons need to be as less as possible. They need to be as less as possible. Now again remember that if you keep very less neurons into the hidden layer, your system is able to get only predictors with very less kind of complexity. So if in this problem I take in only one hidden neuron, it can only predict shapes like this, it can only predict shapes like this, it can only predict shapes like this. It cannot predict anything more than that. And of course with either this or this or this or anything, I am not done. So 1 neuron is very less. So let me increase it up a little bit. Let me say 2 neurons. 2 neurons, possibly my neuron would be able to predict this. It would probably be able to predict this. Again, I make more random guesses over here. So if I say this, it does not do. If I say this, it does not do. And of course, whenever I draw this curve, it means that I will be applying training. So it will try to scale it up, it will try to orient it up, it will try to do all sorts of things, but the basic complexity is fixed. If I increase my neuron to let's say 5, then I'm able to have good shapes like this, and all their invariants, all their scaling, all their ups and downs. So I can have curves like this, I can have curves like this. And that's what exactly is the curve out here. So by slowly increasing, I find out that the actual neurons, I can find out what actually neurons are required. If I change the number of neurons from 5 to 10, I'll have my system being able to predict curves like this, being able to predict curves like this. And that is what will eventually happen out if I overtrain my network. If I have increased the epochs incredibly, then what would eventually happen is that in place of this thing that a neural network with 5 neural layer was actually learning, it will be capable of taking very complex shapes. So in order to even better fit the curves, it will actually learn something like this, which we know is not the case. If I still increase my neurons further, to let's say from 10 to let's say increase it to 20, I'll have a have a neuron that is able to take in more complex shapes like this and like this. So I'll have something like this as my neural network, which is even more wrong. And if I trace it to, let's say, 100 neurons, the neural network will ultimately end up in predicting something like this, which is completely wrong. It can take in any number of shapes. So general methodology would be start up with the lowest neurons and try to increase them as less as possible till you get sufficient output. Don't overfit, don't underfit. Try to generate the ideal fit. And similarly with the number of hidden layers, if I increase the number of hidden layers from 1 to 2 with any small number of neurons, both I will immediately get this curve. If I still add it further, my curve will get even more complex. So this was regarding the output space that I have plotted for the number of hidden layers and for the number of hidden neurons. Now unfortunately it's not known exact and beforehand what the complexity of the system is. It's not known in advance, and therefore you need to actually do a lot of work and try to find out. If you try to train a complex system with less number of neurons, it will not train. If you try to train a simple system with more neurons, it will overtrain. So you cannot start with these many neurons, you cannot say start up with those many neurons. But what ideally we believe is that the number of turns, which of course cannot be defined. It's very easy to measure turns in a one-dimensional graph. It's not a one-dimensional graph, it's a highly dimensional graph. But still, let me say I can define the number of turns is directly proportional to number of neurons. That's why 100 had these 1, 2, 3, 4, 5, 6. 100 had so many 25 turns, and 1 had only 1 and 2 probably had only 2 turns. Number of turns will be in some proportion to number of neurons. Of course, I won't say these are directly proportional, but as the number of neurons increase, the turns increase. As the number of neurons increase, the turns increase. So there is a direct relationship between them. Now, what many people do many times, is that they get this kind of problem. I'll only draw one dimension again, I'll want to draw more than one dimensions, which is like this. So let's say for one input, this is what the output you get. Now again, there's no pattern in this. There's no way that you can find out a trend in this. You take this into a multi-dimensional space. You take it into a highly multi-dimensional space. There's nothing that you can find out over here. There's no kind of pattern that exists. There is no kind of trends that exist. And that's a problem with your, the kind of problem that you're working with. This is not a problem to be solved by any intelligent techniques. Intelligent techniques could have only worked if you had some kind of patterns that could have been deployed, as was the case with my previous curve. It's represent a smooth shape over a multi-dimensional space. But when you plot this space up manually, this is what you ideally get into a multi-dimensional space. Now what many people unfortunately make a mistake, they take in some couple of hidden layers with a heavy number of neurons in each, and as a result neural network does get trained. It gets trained like this. It sometimes gets trained like this. It gives you a very low training error after a heavy amount of training. Now remember, when my number of neurons are very less, the number of training parameters that I have to modify to tune are very less. My error space is of very low complexity, and it's very easy to find out the global minima in a less complex shape. Take any network now. This problem has a couple of hidden layers with heavy neurons in both of them. So I into H1, H1 into HO, HO in H2 into O plus H1 plus H2 plus O plus 1 would be the dimensionality of the space. H1 the number of hidden neurons in the first hidden layer, H2 the number of hidden neurons in the second hidden layer, I in the input and O in the output. Now this is a highly dimensional space. Calculating, fitting this curve will take an intensive amount of time, even more if the number of data is very large. So after hours and hours of training, this is what you will get. And again, if you say that let me calculate the output at any unknown point, so let me calculate the error here, it's all something random in nature. I don't know how it is calculated, but it's all random in nature. So having a neural network trained with utmost difficulty is not a solution to the problem, this problem cannot be solved. You need to change in your attributes. It's probably that you have identified the wrong attributes that do not affect the output. It's that probably some of the attributes that affect the outputs are missing. It's probably that your input attributes are entirely wrong. You have made some wrong assumptions, and that's all. There are so many rules of thumb that exist. So there are some rules of thumb that say that if you do this, these many input neurons, these many output neurons, this should be the ideal number of neurons, but then they are again bound to work. In any of the applications that we consider here or elsewhere, we will not take these rules of thumb to be true. The other important thing is that because I said that there is a knowledge base and there is a database, I mentioned the point that knowledge base is a summarized form of the historical database that exists. Historical database is a bigger form that stores in all the historic base and not was basis the smaller form. The size of the input database that I give is the size of the historical database, and the size of the knowledge base is nothing but the size of all the weights and biases. Now, one thing you will again like to ensure in whatever system that you have got, ideally, when database is redundant, when your historical database is redundant, it contains so many patterns, it contains so many features, it contains so much good of information, that an intelligent technique can be easily applied over it, which is an ideal scenario, which is the qualities of a good database. Your size of knowledge base should always be less than the size of the database, and that's what didn't happen with this problem that I just drew up over here. Having a couple of hidden layers, having so many neurons with so much of weights and connections, so much of real numbers being stored, ideally would have landed up in a scenario where the size of the knowledge base is much larger than the size of the database. So in that scenario, it would have been much better if you would have made a lookup table containing the entire historical database, and of course whenever input comes you try to consult this over and over there. The other small point that I would try to make is use of A and N as classifiers. We'll again look into much detail of it, in fact not use of A and N, use of MLP as classifier. Now MLP is mainly seen as a problem solving technique for the function prediction problem. The entire discussion that I took up here, be it the propagation algorithm, be it the plotting of the database, I always plotted up the input space. I never that is the input output space. I never plotted the feature space that I said would work for the classificatory problem. I never plotted that out. Now ideally when you work with MLP and you work with classifiers, there might be some modifications required at the various ends. There might be some kind of modifications that you need to make at some different levels so that the network behaves better for the classificatory problem, because we know that it has all been designed mainly with the perspective of the function prediction problems. Now sometimes of course what I said that they're taking hard delimiter so that but this only ensures that the hard limiter, the output is that gives you a discrete class, does not give you a continuous value output. That is ideally the requirement. Now I will just might be in a couple of minutes discuss in one scheme that we normally use for when it comes to classification problem. I had input. I had some kind of input that was already available with me and an output that was already available with me. So let me say that there was an input and there was a kind of output that the system already had. My output was a class, let's say class C1, let's say the class C2, and somewhere let's say the class C3. In place of taking this as the output, I basically take in another output. I know my output will always be 1 amongst the set C1, C2, C3 up to Cn. So I say that the output that I am taking, it is a probability of 1 for the occurrence of C1, a probability of -1 for the occurrence of C2, a -1 for the occurrence of C3, and -1 for the occurrence of Cn. For C1, for C2 I will denote it -1 the matching score or the probability for the occurrence of C1, 1 for the occurrence of C2, and minus. Now usually it's not good to say that probability is -1, but for that let me say that in place of probability, that is a matching score, that is taken out to be -1. And similarly, if any output Ci comes, I can state that the output is -1 for the occurrence of C1, -1 for the occurrence of 2, there will be 1 for the occurrence of Ci, and there will be -1 for the occurrence of Cn. This is what it will denote. This is what my basically output will denote. So in place of one output here, I have n outputs over here. In place of one outputs over here, I have one output, n outputs over here. This would be the first output vector, this would be the second output vector, this would be third output vector, and so on till the nth output vector. So the entire database that you gave me in the form of n number of people into, let's say A, the number of attributes as the input, and n the number of people. I'm into some kind of biometric recognition, so I'm using the term people, into 1 as the output. I've converted this output as n into n, where n is the maximum number of classes, where n is basically the maximum number of classes. So MLPs they give in a continuous, they need the output to be between -1 to 1. All my outputs are between -1 to 1. So let me take in using this database what I have just drawn. Let me just take in one of this output, let's say OI, that what OI denotes is whether the person I is there or not, whether it's a person I that is there or not. Let me draw this curve OI with a set of input parameters I1, I2, I3, they remain intact. I'll get this like a curve over here. I'll get this curve over here. So basically my entire problem in which I had to find out the output of a class O, I had to find out the output of a class O given a set of inputs. I have divided it into I have added a layer over here that simply says that I have to find out whether person OI is found or not. This is what I am trying to predict over here. So when I do this, when I break up this problem into this problem, I have n number of outputs over here. So basically what will happen is that my neural network architecture will change. That will get of this form. Let me say these are the inputs. These are all the neurons in the hidden layer. I consider only a single hidden layer. And here I would have some n number of output neurons. This neurons returns the matching score of applied input let me say to the person I, if it was a functional prediction, if it was a biometric recognition problem or the class I. And this is a terminology that we'll be dealing with almost any kind of classifier, any kind of system in a classification problem. It may not give me a discrete output that this is the class, it may give me additional information. That is, it matches 80% to person A, 1% to person B, 3% to person C, 10% to person D, 15% to person E, and it kind of gives me a matching score. So in place of getting out a single output, I have just taken a set of matching scores. All the matching scores to be ideally between -1 to 1. And then I simply take all these matching scores and I say that whatever class gets the matching score, that is regarded as a final output. So if at any applied input over here, I had a matching score of 0.1 over here, 0.05 over here, -0.1 over here, minus let's say 0.89 over here, I had a 0.9 over here, I had a -0.75 over here. this is the class that receives a matching score, and therefore this class, whatever this neuron corresponds to, let me say 1, 2, 3, 4, 4 would be taken as the answer. So this is a slight modification that I have done to solve the problem of functional prediction. This is a very slight modification that I have done to solve the problem of functional prediction, problem of classification. I said in place of taking 1 as the probable output classes, taking 1 neuron, I have split them up across n neurons, and these n neurons, they denote the matching score, and the matching score are always between -1 to 1. And then whenever an input is applied, I just look at which neuron gets the maximum matching score, and I return the index of it. And that's it enough. So it's that, like, by a simple addition of this layer over here, I've gotten a good functionality of classification problem. We'll resolve to what is the physical significance of any neuron over here, OI. So basically in this problem I say O is nothing but I such that OI is greater than OJ for all I not equal to J. It is simply a maths function that is returned. That's how my problem is broken up. From O into a set of OI. I'll just try to explain in what is the physical relevance when we do this when we take an OI over here. Now ideally what would happen is that whenever we apply an input, one of the, had it been perfect learning, had it been a perfect database, had it been a perfect set of features, one neuron would have given an output of -1 and the others would have given an output of -1. One would have given an output of 1, the others would have given an output of -1. But again, this would ideally not happen. This would ideally not happen. So one neuron will get an output that is very close to 1, and the others will all give an output of that is very close to -1. So assuming everything general, let me say that I place a kind of threshold as 0. It can more or less be conveyed that only one neuron will get an output that is greater than 0, and the other will get an output less than 0. So if I plot the output space of one neuron over here, now remember again, if there are multiple outputs, I always go to multiple output system into a single output system. In drawing the input space, I always broke up a single output system into multiple output systems, because I cannot draw multiple outputs in the same axis. I'll need a very difficult time in order to visualize this. In order to do this, that's what I have done. I have broken up into multiple output system. If I draw in one neuron over here, it will obviously represent a curve like this. It will represent some curve over the input space like this. If I say that there is a threshold of 0, and most likely only the final output class gets its threshold designs as 0. When I say that put a threshold of 0, I say that you cut this curve across the line 0 in the output axis. So I am kind of cutting it across a predefined threshold that for some amount of time I'll assume to be 0. I am cutting this curve at the line y equals to, or let's say OI equals to 0. Now it was a curve that was spanned across both the positive and negative side of the axis. I cut it across one single line, that is y equals to 0. I will get anything above that, I will get a curve that is below that. My surfaces are broken into two parts. What I see is that remove the upper part, remove the lower part, and only take the rim on which the cut was applied. And if I do this, I can reduce a 3-dimensional graph to a 2-dimensional graph. I can reduce an input space to a classificatory space. I can reduce an n plus 1 dimensional graph into an n-dimensional graph. I can reduce a 3-dimensional graph into a 2-dimensional graph and represent the rim as this. Now this would be most probably a circular domain over here. I say any point that lies inside this rim is the person OI. So these are all OI. This is the decision boundary. And these can be other person, let's say person 1 over here, person 2 over here, person 3, let's say over here. So I've got some kind of decision boundary. In reality, this threshold will not be applied by this 0. It will be applied by how much this class wins from the next competing class. And that is what, if this threshold is lower than that, you can see much lower region. If it's larger, you will see some larger regions over here. that will move the decision boundary over here. If I had fixed a threshold that was high enough, let's say a threshold of 0.25, I would have got a very small limb over here. So I would have gotten a limb like this that would have made the decision boundary move. Now I'm cutting it across the O-axis and I'm viewing it from between. Up is gone, down is gone. The location at it cuts, it denotes the decision boundary. So that's only a attempt to physically represent what this OI means in this kind of representation that we have just given. If I had just given this kind of representation, it's an OI. Okay, so one very obvious question would be, I'm in this case increasing the number of outputs, and everybody knows that increasing the outputs mean some kind of problem called as loss of dimensionality. So why increase the outputs? I simply do one very small thing. I simply say that my database is in the form of input and output. The output are C1, C2, C3 up to Cn. Let's say my 1 is nothing but 0.1, 2 is 0.2, 0.3 and I don't know n. So let me take it as 92. I had 92 users at 92. They all lie between -1 to 1. And this is my output. Now I have only one output in place of n number of outputs. Curse of dimensionality is solved to a very great extent. So the system should ideally be better than that system. But ultimately what happens is, my neural network output, they are always prone to error. I can always have error. So if the ideal output is 0.05, I can get anywhere between, depending on the ease of learning, depending on the ease of your system, and in this case depending on how good the attributes are, I can get anywhere between 0.6 to 0.04. Now this means a person has changed. For a system that is decently good, for a system that is very bad, I can get anywhere from 0.1 to let's say 0. Now I do not, now my error is even more. Now because of an intrinsic system, this would ideally not work. I'll not always get perfect outputs. Let me draw this thing into the input space. So the output from 0 to 1, the input, let's say I1, and the other outputs are all there. Now let me assume that the features are not ideal. Let me assume that the features are not ideal, so there is a slight intermingle that's possible. So let me say when I increase the in feature 1, keeping all the other inputs attributes constant, if I keep the kind of one feature moving and the other features constant, what I ultimately get is, from when it ranges from 0 to a very small value, it is person who is designated 0.6. If I still move further, it's a person who is designated 0.2. There's no intermingling over here. Now this input at this stage is very ideal. So the third person is found from this region to this region, who is let's say designated 0.8. But then what happens is that there is slight bit of intermingling. So there is this region that both the persons are found. I do not know what happens. And then let's say again the input attributes are very ideal. So the person 0.3 is found anywhere between these regions. Now this is a very sharp curve to predict. You will require a very large number of neurons. This is very easy to predict. So this will this will be the curve over here. It will be very easy to predict. This region cannot be handled by any technique. In fact, even the classificatory models cannot handle the intermingling regions. So this is gone in any ways. This is very easy to handle. Now but the problem comes is that if this person 0.1 by chance over here, and after even a decent distance, it happens to be 1 over here. Now even though this distance is decent, the steep is too large, so this will make the slope very large. And you know, this is very easy to predict, and this is very difficult to predict. This is what we already know. So this will again get problem. The other problem is that if I change in the permutation, if I change in the IDs, 0.01 I make it 0.9, and 0.9 I make it 0.01, everything changes. It's like everything changes it all. So ultimately not a good technique to solve whenever it comes to problem solving, giving numeric equivalence. So we've kind of given some respect to the classificatory problems as well. We started out only with what was known as the functional prediction problem. Eventually we've given up a bit of a touch towards the classificatory problems as well. But what we have, most of our discussion was about, it was only the problem of, it was only about the multi-layer perceptron. Now there are lots and lots of ways in which people have worked over. There are various exciting models that they have formulated. There's much interest that the people have taken in trying to adjust different kinds of problems and trying to address different kinds of problems that different kinds of neural networks face. And hence what they have come out is with a series of models. The series of neural network models, a few of them would be that it's called as a weighted basis function network, called as self-organizing map. These are based on basically unsupervised learning. They can have both characteristics of supervised or unsupervised in nature. Normally we use them in the supervised sense. There's a Hopfield neural network, and all these various exciting neural networks that we've got an adaptive resonance theory. We basically call as a learning vector quantization. This one mainly for the classification problem, this one mainly for the classification problem. This has this can solve both the functional prediction and classification problem, but the main intention is taking in a curve fitting approach. So there is much that is going on in neural network literature that we'll see into the later courses. What I'll end up today with is a simple problem modeling scenario. What it deals with, firstly, define your problem. In fact, this is more of know your problem. You know, if you want to solve a problem, you firstly should know what is it supposed to do. And it's not into neural network, this will get it into any kind of any kind of problem that you solve. You first need to define it. You need to identify clearly the inputs and outputs. And of course, if you identify, you need to model the inputs and outputs that you need to do. Based on that, usually we have a step that is known as because we are now dealing with neural networks, we'll have to make in some kind of database that contains both the inputs and the outputs. You'll have to make in an extensive database. That's what the entire is all about. Now, before making the database, you need to be very sure that the inputs and the outputs are correctly taken. Else, after making the entire database, you'll find out that the inputs are wrong, and then the entire effort of making the database is wrong. How do you get the inputs and outputs? That's by analogy of the problem. That's by understanding what the problem is, and that's why this phase is important. Now the neural network starts up right from here, in which you basically need to, we'll not deal with this step as of now. First, you need to select a model. Normally we try out the model and try to find out the best of it, or sometimes we've got some analogy to it. We definitely try to fix the architecture of the model. Then is when you divide the database collected into training and testing. Training, of course, will be into validation. You train the system. Once you train the system, you calculate testing error. You say whether my system is acceptable, whether it's fine, whether my problem has been solved. If yes, system deliver, or problem solved. If my system is not there, you try to train it again. Might be there was a problem in training. Again, system not acceptable. You try to change the architecture. Changing the architecture also does not work. You tried out various architecture, nothing worked. You try to change the model. You try changing the model as well, nothing worked. And then you that probably there's some kind of problem in this problem cannot be solved. You will unfortunately have to resort back that your understanding of the inputs and outputs are wrong, in which there's some kind of problem with the inputs and outputs, and that's how you basically work apart. This is a consuming job because there's a database that's already involved in between. Sometimes in face recognition problems, you can of course work over because facial photographs are already there and the inputs and outputs need to be extracted from there. So then is when you do not need to make in the database again. But if here it does not solve, you will have to accept that all systems cannot be modeled. That everything cannot work. So we'll try upon, we already touch upon this thing, we'll touch upon this thing into the later stage of the course, that is the next lecture, where we'll see the different neural network models. And this, of course, we'll touch upon entirely into the application domain.